actually this is 112. Page 112, number 2. It's a free response. So it tells us sand is being poured into a bin that is initially empty. That means that at time equals 0, there is 0 sand. During the workday, and our time interval is 0 to 9, including the 0 and the 9, the sand pours into the bin at a rate. Now, one thing I want you to see is they've written this as S of t. Now, when you look at this function, you would think that this is not a derivative function. You would think that this is an original. But there is 2 clues that that's not the case. First, if we look at these units, it's cubic meters per hour, which screams rate, and then it says into the bin at a rate given by. So this is the in function. Then after 1 hour, so for an hour, sand is pouring in. After an hour, sand is starting to be removed, and notice this is also just R, and that's going to be 23. By the way, this was a calculator question. They would not expect you to not use one. And again, this is cubic meters per hour, and that's your out function. Both of these are derivatives because they are rate functions, but they don't look like derivatives because you don't see the derivative sign. So how much sand is poured into the bin during the work day? All right, so unfortunately, we cannot do part A because that requires an integral from 0 to 9. I think this may be one we can't do. Find S of 6 minus S of R and include units. All right, so now part B we can do. Literally, S of 6 means you are supposed to substitute 6 into this function. So we have 6 cubed plus 50. And when you substitute 6 in, you will get 18.796 equals 18.7969, so I'm going to make that 7. And if I put 6 into R, that's going to be 23.9665 square root of 6. And that is 58.705. All right, so the goal here was to subtract these two. So notice they had S first. So I'm going to subtract. And this is going to be a negative answer. Negative 39.909. All right, so this is going to be cubic meters per hour because it's a rate minus a rate is still a rate. And what does this mean? This means that the amount of sand in the bin is changing. Notice I word they use changing at a rate of negative 39.909 meters cubed per hour. Now, I could have said that the amount of sand in the bin is decreasing at a rate of, but then that should have been positive if I use the word decreasing. So in other words, more sand is being taken out that is being put in. Explain why the amount of sand in the bin is at a maximum when S is equal to R. So we have, for 1 hour, sand was going in without any removal. After that is when we started to remove. So when the amount of sand that's in there is equal to the amount of sand that is being taken out, that's going to be the maximum because the amount of taking out is being removed more. So what I would do is I would, in my graphing calculator, I would put the S function in. and then I would see the s minus the r function. Remember, this is a rate. And when you go to graph it, and I'm graphing on my calculator. All right. So I think instead of what I'm going to do, I'm going to graph each one of them separately. So I put s of t in y1, and I graph them. And I'm going to increase the y's. Probably should be doing this in the computer so you can see it. All right, so let me try to do that so you can see. If I were to get the calculator out, all right. So you're going to go to y equals, you're going to put the s function in, divided by, notice my use of parentheses, that's important. And then I'm going to put the other one in, if I can find it, 9665. And now I'm going to take my window, my y's need to be, I think I'm going to take it to 100. Well, we'll take it to 111. All right, so this graphed first and this graphed second. This is the rate function of how much sand is being put into the bin. This is what is being removed. So if we look at this area right here, more sand is coming in because the s function is above the r function. Over in this section, the r function's bigger than the, or higher I should say, than the s function, which means more is being taken out than being put in. So that point right there is going to be the point where there's going to be a maximum amount of sand, because the amount going in is greater than the amount going out. And once you get past here, then the pile starts to decrease. So that is what you would explain there. They want to know how much sand in cubic meters is in the bin at the end of the workday, and that would be the integral of s minus r, but we can't do that because that requires a definite integral. So you could do two parts of that 112. Now when we go into section 113, page 113, as I say, the next one we cannot do. All right, 113, number 3, we have a function, piecewise function is shown. So the first thing they've said is the limit exists at 3. It is 1. Okay, if we look at the graph, the y value is 1. The limit is 3, because remember the left, we don't care about what y is, it's about what y is approaching from the left and the right. So the limit at 3 is 3. The y value is 1, so A is incorrect. So if we look at B, if we approach 4, they're saying that is 3, but the problem with that is the limit doesn't exist because the left limit is not equal to the right limit. They're saying that the function's continuous at 3, and there's a hole, so that is not. D, f of x is continuous at 5. That is correct. And then the limit of f of x as x approaches 6 is not the y value at 6 because there is a gap. It does not exist. So that one probably should have been relatively easy for you all. On 17, page 117, number 12, the graph of f of x is shown. So it's important that you realize that that's the original function, not a derivative. We have a closed interval. And if f is continuous and differentiable, then there exists a c between negative 7 and 7 such that, all right, this is screaming mean value theorem. Just looking at the picture, for me, screams mean value theorem. So this is, oh, they even gave us ordered pairs. There's negative 3, 4. Here is 7, 2. So we know that the slope of the secant line is going to be 2 subtract 4 over 7 minus a negative 3, or negative 2/10 or 1/5. And the mean value theorem says if the function is continuous and differentiable, which they gave us, that the slope of the secant line must equal the slope of the tangent line. Slope of the tangent line, by the way, is called the derivative. So if I look at my multiple choice answers, I should be looking for f prime or y prime equals 1/5. So that answer would be C. So now we're going to go to page 118, and we're going to look at 13. Oh, I like 13, and I bet 13 you found to be easy. We practiced these. We had a whole worksheet on these. We have f of x is x squared plus 3x. So here is, this is number 13. G of x and its derivative are given in the table. They want you to, if h of x is equal to f of g of x, they want the derivative of h at 2. This is chain rule. So the derivative of h is going to be the derivative of the outside times the derivative of the inside. So since they want the derivative at 2, we put 2 into x, and we look at our table to find g prime of 2. So we go over to x equal 2, the derivative is 3, but we also need the y value at 2, and that is going to be 1. So now we've got the derivative of f at 1. See this? So now I've got to do the derivative 2x plus 3. So now I'm going to put 1 into the derivative, so I get 2 plus 3 equals 5. So we're going to have 5 times 3 equals 15. All right, and then on page 119, we've got number 16. Ooh, look at that. Another related rate. All right, so 16, the volume of an expanding sphere. Volume is expanding at a rate. That's going to be dV over dt. That's 12 cubic feet per second. When the volume of the sphere is 36 pi, how fast in square feet per second is the surface area increasing? All right, so we know our volume. We know our volume formula would be 4/3 pi r cubed. So I'm going to divide by 5. I'm going to multiply by 3/4. 4 goes into 36, 9 times 3 is 27. What this gives me is this gives me r. So r is equal to 3. All right, if I were to go ahead and go over here and start my surface area, I'm going to have 8 pi r dr over dt. They want to know how fast is the surface area changing. All right, this is the issue. I've got my r, which is 3, but I don't have my dr over dt. So I was sitting here wondering, why in the world did they give us this information right there? And the reason why they gave us that information is because that's how we're going to find dr over dt. So we know dv over dt is equal to 4 pi r squared dr over dt. All right, our volume is 12. Our radius is 3, but that gets squared. So we're going to end up with 12 is equal to 9 times 4, 36 pi. So the rate of change of radius with respect to time is going to be 12 over 36 pi, which is the same thing as 1 over 3 pi. So now I can come back here, put 1 over 3 pi in, and look at that, they simplify. So the rate of change in the surface area with respect to time is just 8. All right, so now we're going to go to page 121, number 20. and we have a function that is differentiable on the open interval. That means it's also continuous. We know that it has a minimum, CF of C is a minimum, and we know that this C is somewhere between A and B inside that interval. So which of the following must be true? All right, they're telling us that f prime of C must equal 0. All right, this is saying the derivative is where we find critical numbers. If this point at C is a minimum, then it had to be a critical number. And it can't be a sharp turn because the direction said it's differentiable. So it's definitely number 1. Now they're telling us that the second derivative must exist. All right. So they told us that the function's differentiable. They did not say twice differentiable. So there's nothing here to suggest that that's possible. There's no guarantee. So that's a nix on 2. And then 3 says if the second derivative exists, then the second derivative of C has got to be greater than 0. In other words, okay, so this is where they're coming from. They're saying if it's a minimum, then the second derivative there must be greater than 0. In other words, it must be positive. And at first glance, you would think, well, that must be the case. If we look at, let's say, x to the 4th as a function, if we do its derivative, remember there are 3 possibilities. The second derivative could equal 0, and the second derivative could be less than 0, and there's your other one is the greater than 0. So remember, if the second derivative equals 0, then it still could be a minimum, but the second derivative test fails. So I'm giving you an example of if I were to set this, so if I do a second derivative, this is going to be 12x squared. So if I were to set my 4x cubed, my first derivative equal to 0, I get x equals 0. Now if I do a little table to find out its max or min situation, let's do 1 and 2, then the first derivative is going to be, oh, that's going to be negative 1. The first derivative is going to be negative. The second, when I put 2 in, it's going to be positive, which means my function's gone from decreasing to increasing. So at 0, there is indeed a minimum. But if I put f double prime of 0 in to the second derivative, I don't get a positive. I get 0. So what this statement looked good initially, but it's not because there's no guarantee that it's greater than 0. It could equal 0. So we cannot verify 3. We do not know, so only 1 for sure is accurate. So that was 121. We're going to go to page 124, number 26. Oh, I have prepared you for this. I have prepared you very well for this. So, and this is, notice they've gone a step further than what I've done with you all. This is tan of 2 times x plus h minus tangent to x all over h, where h approaches 0. So this is the definition of derivative. Now, because this is not a single number, all we can tell from this is that the function is tan of 2x. Remember, we take the x plus h out and replace it with x, so that's going to be tan 2x. This is a number if we knew x, but we don't know x. So what they did is they subtracted f of x, which is tan x. So now, what this says is, this is basically saying take the derivative. This limit would be horrible to do, but it's a derivative. So all I have to do is the derivative of this function. And the derivative of tan is secant squared of the angle. And notice this is out, and this is chain rule. And the derivative of 2x is 2. So on 26, your answer should be D. All right, so now we're going to go to page 134. And 134, we are doing problem 44. It says f is continuous. That's a key word. It's also odd, meaning it has symmetry around the origin. And the limit, oh, that odd is really important now that I see this. The limit of f of x as x approaches negative infinity is negative 3. Let's remember odd. So here's 44. So if I were to draw a picture, and I were to draw a horizontal asymptote, because that's how we get horizontal asymptotes or limits to infinity, I think this would, let's see, or odd means that it crosses through the origin. I believe that this graph right here is a good graph to describe what they have there. Now remember, it's odd, which means that we should be able to take this and we should be able to rotate it about the origin. So if I rotate it about the origin, then it's going to be up here. So notice this is also going to be approaching something, but it's not going to be negative 3, it's going to be positive 3. So they're saying in part A, they're telling us that the limit as x goes to positive infinity of f of x must be 3. That is correct. So 1 is good. There are no vertical asymptotes. I don't believe there's anything there. The fact that it says continuous would indeed verify that there are no vertical asymptotes. So far 1 and 2 are good. Now it says the lines y equals 3 and y equals negative 3 are horizontal asymptotes. That is also correct. So on this one, all 3 are correct. And I asked you to go to page 145, which finishes this part of the exam review.